Hey everyone, welcome to this talk. In this short video, I will give a brief introduction for our paper in ECCV 2024 this year. Our work is titled as Stitch ViTs as Flex-Oriented Backbones, and my name is Jinpan from Monash University. So as most of you already know, adapting large pre-trained vision transformers into dense predictions is computationally expensive, especially when training a large model like ViT large. When training this model on Coco Staff 10K will take 98,100 GPU hours. So after training, it also suffers from a fixed speed and performance trade-offs. So a possible solution to address this challenge is by using stitchable neural network. So the main idea of SNet is that we can directly stitch pre-trained small and large ViTs together and jointly train this network with some fine-tuning to obtain many speed and performance trade-offs. But SNet V1 only experiments with pre-training data domain. So the question is, can we use SNet V1 to obtain numerous trade-offs simultaneously on downstream dense predictions? Well, technically we can, but SNet V1 is not ready for downstream dense predictions. So because fine-tuning on the same original dataset as anchors can be impractical due to exceptionally large dataset. Second, small space resulting in suboptimal performance and efficiency trade-offs and bad frontier on dense predictions. So in the figures below, we can clearly see some bad trade-offs by using V1 on both ImageNet and AD20K. The latter is a dataset for semantic segmentation. So in this paper, we first address this challenge by proposing a novel two-way stitching. The main idea behind two-way stitching is enabling the network to go from the small model and down to the large model, then back to the small model again. And we can also do reversely. So essentially, this strategy can achieve 10 times the larger stitching space. So for example, in this comparison, we can find the clear improvement over most trade-offs at the high flops range, but there is a huge drop at the flops of the small model. Well, with further exploration, we find the issue arises in the imbalanced sampling of subnetworks after enlarging the stitching space. So initially, the random sampling works very well in SNet V1, but after enlarging the space, the anchors are significantly less sampled than before. So this has encouraged our second improvement called resource-constrained sampling. So the idea is pretty simple. First, we uniformly sample a target resource constraint from a predefined table. And second, we can then randomly sample a stitch that satisfies that constraint. So with this improvement, we get a very smooth parallel frontier by training on ImageNet. So now let's experiment on downstream dense predictions like AD20K. So actually, if we directly adopt our new framework on AD20K, there is a very bad frontier. The reason could be that the activation space changes more significantly on target domain than the pre-training domain, since training on AD20K is a completely different objective than that of training on ImageNet. To address this challenge, we propose to use low-rank fine-tuning to stabilize the overall training process. So now with the LoRa stitching layer, we retain the smooth parallel frontier on downstream tasks as well. So in our main experiment, we get consistent better frontier than SNet V1, and this figure compares SNet V2 with V1 on two semantic segmentation tasks. Most importantly, training on SNet V2 directly obtains hundreds of trade-offs. At the same time, the overall training cost is less than that of training a large vision transformer. This is because during training, we sample networks from a range of flops constraints instead of always training the single large ViT. In conclusion, we improved SNet V2 on dense predictions with three tightly coupled components: a two-way stitching, a resource-constrained sampling, and a low-rank adaptation of stitching layers. So currently, the framework still requires a small ViT, so future works might explore the possibilities of removing the dependency on small ViTs. So that's all for this talk, and if you are interested in our work, feel free to scan the QR code below and check out more details. Thanks for watching.